Okay, so let's start our lecture today. So, uh, okay, so, okay, yeah, so, so let me draw this. Uh, so you have region 1, 2, 3, 4, 5, 6, 7, 8. Okay. So okay. So and yeah. So this is like omega 1, and here is like so omega 1 tilde and omega 2 tilde. Okay. 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 So in 2. So okay, so we have a total sum. We have the total sum as so summation n from 1 to infinity, summation of m bigger than or equal to n times modulus of omega 2 tilde over this modulus of omega 1 tilde. And then this 4mn a1 a2 minus 2i n square a2 square minus n square a1 square, okay, over 4n square a2 square plus n square a1 square square, okay. And wait, I think I miscopied it. So yeah, sorry, this is in 8. Okay, so this is in 8. Okay, so in 2, so we have the sum as yeah, so summation and from 1 to infinity of summation n bigger than or equal to m times modulus omega 1 tilde over modulus omega 2 tilde. Okay, so negative 4mn a1 a2 minus 2i times this n square a2 square minus n square a1 square, okay, over 4 n square a2 square plus n square a1 square, okay. Okay, so how do we cancel this one? So okay, so let's see. So okay, let's think about it this way. So okay, so either we have okay, so if we have m bigger than or equal to n modulus of omega 2 over modulus of omega 1, right? Okay, so this is the same thing as, so this is a equivalent of saying that, so this n is, wait, so when we multiply by the inverse, okay, so we multiply by the inverse, n times modulus of omega 1 over modulus of, modulus of W1 tilde over modulus of W2 tilde. Okay. Okay. Yeah. So I think in this way we can also, because is this one the same as if we sum over, let's see, so okay, let's see, so here we sum from m from 1 to infinity, right? It is the same, and then I sum over is n less than or equal to, oh, okay. Oh, okay. Okay. N less than or equal to n times modulus of omega 1 tilde over modulus of omega 2 tilde. Okay. Oh, yeah. So I think this is the same. So, of this, oh, but wait. So here, okay, there's, so okay, I want to be a little bit careful here. So, okay, so, okay, so why did it shoot? So, I think it's a different way of doing it, right? So, namely, so this n is associated to what? So this n is associated, okay, so, for each of the term that appears here, right? Either m is bigger than this n factor. Okay, so you have m is bigger than this guy. N from 1 to infinity. Okay, for each of the n's bigger than that. Okay, well, n sum from 1 to infinity. M is bigger than that. Okay. For each of the n, m is bigger than that. So, great. Okay. So I think this is the same thing as uh, okay. Yeah, I think they are the same. Okay. Okay. Yeah. So for n a1 a2 minus n2I n squared a2 squared minus m squared a1 squared. Okay. Okay. Yeah. Okay. So yeah. So this guy. So yeah. So when you sum them up, right? So okay. So let's arrange it in this way. So think about the if you have yeah, so let's think about like splitting it into two parts. Okay. So let's think about this part. So for the imaginary parts, okay. So for the imaginary parts, I can split it up as negative 2i. Okay. So imaginary okay. So I can split it as negative 2i times the sum of, so these are all the n's, right? Okay. Wait. Okay. Okay, so let's assume that wait. Oh. Yeah, let's assume that okay. So this m times modulus of omega 2 over modulus of omega 1 is not an integer. Okay, so that we can just easily handle the sums here. So this is like n from 1 to infinity, m from 1 to infinity of just n squared a2 squared minus m squared a1 squared over 4 times n squared a2 squared plus n squared a1 squared. Okay. Yeah. Okay. I think for each m, right? So for each m, so this is yeah, it converges. Yeah, but what about if this m is being summed? Will it still converge? Is there any theorem I can use? Okay, so is there any theorem I can use for this one? So, let me think. So this is a double series. Sweeney. So this is a double sum. So what happened for the double sums here? Why don't I do an integral test to see if it converges or not? Okay, I think that's a really good idea. Okay, so let's see if I can do an integral test. Wait, for the integral test, I need a function to be strictly decreasing, right? Yeah, I think, wait. I think when you, yeah, so when you increase n, it is like strictly decreasing, right? And then when you still increase this m, for each of the, after you sum the n, right? So for each n, I know that it is converging. So, and then after that, you increase the m. For the denominator, you may get something negative. Wait. There might be a imperative type, I think. So this one is not positive, right? So if you're increasing the m, I think this is a problem here. yeah, so for the integral test, right? I know that for each n, I can apply for each n, I can, if you fix an m, right? So I can apply the integral test. So what happens if you after you apply each n, you get a number, and then what about the m's? For each m, you are getting this number here, right? And then so this is like this number minus. Oh, okay. Oh. Yeah, so for each m, you are getting this number, right? And then this m is, when m increases, the bottom one, the denominator is getting bigger and bigger, right? So I think that's the key part here. So because the denominator will, so the numerator is getting more and more negative, right? But in a way that's not gonna sort of influence the result. So, so there is a constant. Okay. Yeah. So it's like, because I know that for each of, if you fix an n, then this n will converge, right? So it's like, yeah. So it's like from one to infinity. So for each of m, there is some constant number, okay? Cm, right? Yes. And then, wait. What number will it converge to? Wait, we don't know. We don't even know the expression, right? Okay. So the question is that, what do we know about this Cm? So we know that it converges. So the question is that, can we use the integral test? Okay, so the question is that when this m is increasing, right? So with this constant, either it would, I think, if this constant is negative, right? So I think eventually this constant might be, why this constant might be negative? Okay, so I think for each m, right? Yeah, so I think for each m, this Cm must be positive, right? Wait. There's no, wait. So for each of the Cm, what do I want to say? So so what do you want to say? So for each of the CM, so does it converge absolutely? Okay, so for each of the CM, you sum it over n, right? I think if you sum over n, so eventually this term will be positive, okay? So maybe there are like some terms that for some n, right? So this sum is negative, but eventually the tails, yeah. So the tails for each term, for each m, okay. So for each m, so the tail part of the series of let me use a number here. So this n really depends on m, right? Maybe let's use this, okay. Of this n square a square. Yeah, the tail part of the sum over 4 n square a square plus n square a1 square are all positive, okay. Let me see. Is it recorded here? Okay, good. So, yeah. But I don't think that's necessarily mean that the whole thing must be positive, right? So what I want to show. So, if I let m runs, okay. Oh, excuse me. Yeah, so if I let this m runs, then if I only look at the tail parts, right? So namely, I can break this Cm into two parts, right? I can break this Cm into a Cm head part and plus this Cm of the tail part, right? Where the head part is the part that this sum is negative, and this part is the part where the sum is positive, okay? And Okay, so for the tail part, okay, what I do is that I'm gonna okay. So for the tail part, I'm gonna so for the tail part, I'm allowed to use the integral test. Okay, I'm allowed to use the integral test. Wait, but then, shoot. So what does the integral test says? So, yeah. Okay, I think I'm allowed to use the integral test, right? Because this function is not alternating. Okay, so this function is not alternating, so therefore I think I'm allowed to use the integral test. So why, if it's not alternating, I'm allowed to use the integral test? Because so the integral test says, so if the function is decreasing and wait, what about the approximation here? yeah, so why am I allowed to use the integral test? Yeah, so if I fix an n, so when this n is like increasing, okay, so if I fix an n, this n is like increasing. So the denominator is getting like very like bigger and bigger, right? And then the numerator, so the numerator will be initially it might be negative, right? So initially, if n start at 1, if m is like 1, yeah, so initially it could be a2. Yeah, initially it may or may not be. Yeah, I think initially it must be negative, right? Because this a1, yeah, this m, this initially it will be negative because this a1, I'm assuming that this a1 is bigger than this a2, right? Okay, so initially it will be negative, and then after some term, it will become positive. Okay. So initially it will be negative, but it will be okay. It will be less negative. Okay. It will be, so the function itself will be wait. Why will it be increasing or yeah, so yeah. So it will eventually be decreasing, but it might have some yeah, it may have some dip here. So why I'm not allowed to use the integral test? Okay, I'm allowed to use the integral test because I'm just trying to state whether this integral is converging or diverging, right? Because for the tail part, okay, because it's eventually, why is this eventually decreasing? Okay. Yeah, because it's converging to 0, right? It converges to 0. Yeah, so it must be. Yeah, so if you divide by n squared on both sides, right? So eventually the denominator is getting bigger and bigger, right? Yeah, so the denominator is getting bigger and bigger. Okay. The denominator is getting bigger and bigger. So therefore it is eventually decreasing. Okay. So applying, so the finite part is always finite. Yeah, because I'm always wait. Yeah, so this test, I think it applies to the, if you fix an m, then I think you are able to apply the integral test for each n. But what happens if they come together? Why am I allowed to apply the integral test? Yeah, so there is this finite part that's kind of bothering me at the beginning, right? Because if I want to apply the integral test, so why am I allowed to apply the integral test at the beginning? Yeah, so at the beginning there might be some negative part, and then it's so the negative part, if I take the integral, right? The integral, I know that at the beginning part, because for the numerator, right, so it's getting smaller. And then when the numerator is getting smaller, okay, so for each of the term, so the numerator will be less negative, okay. And then the denominator will be also larger. Okay, so here if you're comparing the two terms, so for numerator you will have a less term, and for the denominator you will have a bigger denominator. So the absolute value, right? So if you compute the absolute value, it will be lesser. Okay, so therefore this is strictly increasing. Yeah, so this is strictly like increasing like that. And then when you are trying to do the, so let's see, so it always start at 1. Okay, so it starts at 1 here. Okay, so okay, so let's integrate from 0. Okay, so I think we can always integrate from 0. No, we cannot integrate at 0 because of this behavior, right? So when we integrate from 1, so I don't think we are allowed. There's a guarantee that okay, so I think if it start at 1, do we need some yeah, so here we may have this because it's increasing, right? Oh, okay. Yeah, because it's increasing, so the integral will be higher, will be above. Okay. The integral will always be above. Okay. So what happened at this point? Okay, I'm just wondering what happened at this point. So if you take a value here, oh, okay, I see. So yeah, so at any point, the integral value, the function value will be always, so if you interpret the m and n as like this x and y here, so the function value will always bigger than the, so interpret this one as like a characteristic function. So this function value will always be bigger than or equal to this characteristic values based on this m and n. Okay. Okay. Wait. I was a little bit confused. So this is like, okay. So yeah. So this is like. Okay, so at least I know that for this one, right? So we'll think of this n as like that, okay. Like for fixed m, okay. So this is m is like fixed, okay. And then, so when you're increasing the function here, increasing the n here, so basically, so if the function is bigger, so the question is, oh yeah, I think so, right? Because the integral, yeah. So if you take the yeah, so the okay. So I'm claiming that, so the integral of this function, right? What I'm trying to say. So why is true? So yeah. So let me think. Sorry. So yeah. So yeah. So my interpretation basically is that if you are using the integral as the area under the curve, right? So this area will be less negative than this. Oh, okay. Yeah. Okay. Sorry, let me see. Yeah, I think so yeah, I think in terms of the Riemann integral, okay. So this value, okay. So if we consider this value as, let's say, so this f minus, right? So this f minus. So I'm just fixing m, okay. So let's just think about if you're fixing like m values. So this is like m values here, okay. So fix m value. So then maybe that, yeah. So yeah. So fix the m value, okay. So think about like y equals 1, y equals m here, okay. So and then okay, yeah, and then what we have is that yeah. So this negative parts, so when we like tilt it around, like make it like positive here, and then so this is actually a partition that's what I can say. Yeah, this is the characteristic function that's bounded above, right? So bounded above. So yeah, so wait, what I want to say? Yeah. Yeah, so let's just think of it m, okay. Yeah, as single m, okay. Yeah. And then I'm claiming that this f minus of x. So this is if you like view like the yeah, so f minus x, I think you think of it like a positive one because this f literally is f plus minus f minus, right? So I think so this one, yeah. So this one is actually a yeah. So this one is a characteristic function that. Okay. Yeah. Yeah. So it is. I think it's being defined as the infimum, right, of all the characteristic function that's takes value. Let's see what. Takes value. I think this is just bigger than, okay. So this is just bigger than the f. Okay. So like integral of phi bigger than this f phi simple function. Okay. 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 Yes. So therefore, yeah. So therefore, oh, and also same for this one, right? Yeah, I think because of the I think wait. I think yeah. I think there's a theorem about also yeah. Okay. Oh, okay. Let me think. Yeah, I think by some argument, like you can sort of show that like this infimum is strictly bigger than the supremum of this lower partition. Yeah. So yeah. Okay. So yeah. So in this case, okay, I think you can somehow show that. So this is like, yeah. So think of this one as like a character, like phi, okay, like this characteristic function here, and then so I'm saying that if this phi is less than equal to this f, then the integral okay. Okay. Integral over this r of phi is less than equal to integral over r of this f. Yeah. Whenever it's defined. Okay. So yeah. Okay. Because because yeah. Yeah, at least in our case, okay. So in our case, I think this is true because maybe maybe I would say like in this case, okay. Yeah, in this case, okay. So we have the integral from 1 to infinity. You think of this one as a we define it to be even sum here, okay. And this one we define to be the improper interval, okay. Okay, so I think this is true because I think like if you think about like this f as s plus and f minus, so for f minus, you can show that this one is so you basically you break the phi into like two parts, right? So like here there's a splitting point here, okay. So you can figure out yeah. So there must be like a point where the number is like positive, right? So yeah, and then so therefore yeah. So therefore you show this phi is sort of yeah. So the f negative that you flip it, right? So this is like f negative, and then you have the phi is like bigger than this f negative, right? So the integral of phi is actually bigger than this integral, like integral of f negative. And but then when you take negative, then you see that this phi is actually yeah, we will make it negative again. So because yeah, we will make it negative again, and then so this is this f is strictly bigger than this negative f minus is bigger than equal to, is bigger than the negative of this phi here. Okay. So therefore you have like a one thing, and then yeah, and then you also have the improper integral, which is also bigger. Okay. Yeah. So therefore, yeah. So therefore you have this one. Okay. Therefore you have this one. So. Yeah. Okay. Yeah. Therefore you have this one. Okay. So. Yeah, so in this way, I think, yeah, so you can apply the integral test in this one, okay. So what about the m's here, okay. Can you do the same thing for this m? I was a little bit curious. If you sum over this m here, so what would happen? So yeah, so this is a simple function here. So yeah, so if you view this n and m as yeah, so if you wait. Yeah, so if you view this n as this x here, and then this m as like the y, so you think of that this is x, and then you think of the y as going in this direction, like going out, and then let me think. So what would happen? Oh, okay. So if you increase the y value, right? So if you increase the y value, oh yeah, I think that's the problem. So if you increase the y value, then you'll be getting. Wait. So if you're increasing the y value, would you get? If you fix an n here, and then so initially, if you are, yeah, it will be smaller, right? It will be smaller. Wait. If you fix an n and then you increase m, okay. If you fix an n here and then you increase m, what happened? So, yeah, say it into 1. So then, get n into m becomes m from 1, and then say it's negative, and then if you increase it, it becomes more negative. Hang on. Hold on. If you increase m, what will happen? If you increase m, what will happen? So if you increase m, okay. So if you think of the absolute value for the numerator, the absolute value will be bigger. Okay, so the absolute value will be bigger, but the denominator will also be bigger. So I believe that eventually it will be, yeah. So I believe that eventually it will be, Wait. Okay. So if you okay. So wait. Oh, okay. Wait. Okay. I was a little bit suspicious here. So, yeah. So let me just erase this one. Okay. So, do I need to erase this one? Okay. Let me just erase this one. Okay. So, so if I divide by m on both sides, okay, I'm getting, okay, so if I divide by m on both sides, okay, so I'm getting n squared over m squared, a2 squared minus a1 squared. So this number is less than, yeah, so the m increase is less than 1, okay, and then what's inside here, okay, so here you will have 4 times if you divide by m squared on the denominator, you will get 4 times, let's see. So here is like n squared a2, sorry, let me just expand this one. Okay, so n to the fourth power, a2 to the fourth power over this m squared plus so 2 n squared a2 squared a1 squared, okay, plus so this is actually m squared a1 to the fourth power, okay. So when I increase m, so the denominator I know will be strictly bigger, right? Y is strictly bigger. So so this one is, so when a equal to 1, let's say when a equal to 1, okay. So let's say n equal to 1. So this is just a2 to the fourth power over m squared. So when I increase m, this a2 to the fourth power over m squared is being less, but this m squared times a1 to the fourth power is very big. Okay, so so this case I think there might be some dense, it might be some oscillation happens. So in this case, can I still apply the integral test in this scenario? Okay, maybe I'm running out of time. Okay, so I will try to continue to analyze this case. Okay, so see if I can apply the integral test.